In the 18th century, the high altitudes of the Swiss Alps served as a laboratory for a specific mission. Explorer Horace Benedict de Saussure climbed these peaks to definitively measure the color of the sky. He used an instrument of his own design, the cyanometer. This circular card features 53 distinct shades of blue, arranged in a gradient from nearly white to a deep, heavy black. As he hiked higher, Saussure discovered a distinct pattern. His measurements dropped rapidly down the chart, moving closer to the absolute black of the void with every 1,000 feet of elevation. Space is a vacuum. As we see with this astronaut on the moon, brilliant direct sunlight can hit the ground, while the overhead universe remains pitch black. The cyanometer captured an active, localized physical process. This blue is a unique signature of the invisible space occurring around our heads. Sunlight arrives as a concentrated package of energy. A prism reveals its true identity, a fanning spectrum of highly saturated colors. This comparison shows how that light travels in waves. Red light stretches out in long, slow-moving undulations, while blue light takes the form of tight, rapid waves packed with energy. Before hitting the surface, this radiation must navigate a dense jacket of trillions of nitrogen and oxygen molecules, creating a microscopic obstacle course. British physicist Lord Rayleigh calculated the rules of this environment. He proved a light wave's physical size dictates exactly how it interacts with these particles. This animation illustrates Rayleigh's formula. Slow, heavy red waves glide past the tiny molecules undisturbed. But the short, energetic blue waves strike a nitrogen and oxygen head-on, violently ricocheting in every direction. Looking up, you are seeing a planetary-scale collision zone, where trillions of short wavelength waves are diverted into your eyes. Distance alters the scattering. Midday light drops straight down. At sunset, light takes a horizontal path through 10 times more atmosphere. The blue waves are entirely filtered out into space. Only resilient, long-wavelength red waves survive to hit the surface. There is a mathematical challenge. Violet light waves are shorter than blue and scatter more efficiently. By Rayleigh's math, the sky should be purple. Sunlight is imbalanced from the start. Our star pumps out significantly more blue radiation than violet. The rest of the explanation lies in human anatomy. Cone cells in our retinas are uniquely tuned to blue light. When the eye receives a mixture of blue and violet, the brain processes the signal as a clean, pale blue. The sky is a biological translation, a compromise between the physics of our local star and the evolutionary wiring of our own nervous system. Because this effect relies on the specific size of gas molecules, changing the debris in the air breaks the math. Thick water droplets are so large they scatter all wavelengths equally, merging the spectrum back into flat white clouds. Geological events can erase the blue. A massive volcanic eruption blasts millions of tons of heavy aerosol ash into the upper atmosphere. These particles swallow the blue and green light, leaving behind blood-red skies for months. A different chemical makeup yields different physics. Mars has a thin atmosphere of carbon dioxide filled with iron dust. Standing on this surface, you would see a pale butterscotch horizon. When Saussure held his card to the heavens in 1789, he was auditing the chemical balance of Earth. Clean, nitrogen-rich air is a requirement for this specific scattering process to function. The blue sky remains a fragile, continuous performance. It exists only as long as this specific balance of gas and light remains in play.